names on this title slide because this is a talk from the section. And if we included all the collaborators whose work is reflected in these slides, I wouldn't get through the talk. Many of you are here. The talk was specifically designed for our CISL colleagues. It is a CISL seminar. And so I start subtracting my team and our science collaborators. There's about a dozen, maybe, CISL folks in this room. This seminar is for you, okay? So I encourage you to ask questions, as many as you want during the thing. The rest of you know where I live, so technical science questions, no, that's not what this seminar is designed for. I'm happy to talk with you afterwards. So, a quick outline of what we'll be doing. I'm going to briefly introduce what ensemble data assimilation is. That'll lead into the data assimilation research test bed, which is the software and stuff that we do in DARES, the data assimilation research section. The biggest part of the talk is going to be a series of 8 collaborative projects, and those projects will introduce collaborators, DARES team members, particular capabilities of ensemble data assimilation. And so they're going to try and do this matrix thing where we hit one of each of those types of things. And so you'll see what that's like when we get there. If there's time, and for the CISL audience, this may not be as appropriate, I may briefly talk about some of the data assimilation science we do in DARES. And then at the end, a little bit about some exciting new projects that we're going to be moving on to in the near future. So, data assimilation. This was actually one of the first slides we made for DART in 2002. And since we're supposed to give the source of these things, I have no idea where these things came from. So it's a thermometer. And so data assimilation is combining observations or measurements, as they're more commonly known outside of our Earth system, with a computer forecast model. We all understand that. And so you combine those two pieces of information to produce a better estimate, often called an analysis. And that analysis can then be used to start more forecasts that can be combined with more observations in the future. And the way we do data assimilation is this sense of sequentially cycling through that. So ensemble data assimilation, and you see the first hint of that in the lower right panel here. That's a topographic map of a pressure surface in the atmosphere, a 500 hectopascal height map. And instead of a single contour, there's a bunch of contours for each one. Okay? You wouldn't want that if you were hiking, okay? But we might want it here, and that's because there's tons of uncertainty going on in what we do. So our observations are uncertain, of course. That's a universal thing. So thermometer out on the roof here on the pole, it's not exact. It's got some error. That error varies in time. We don't have as many observations as we would like for any of the problems I'm going to talk about. It's a really big world, and so you can't instrument everywhere. And another issue that's really central to the way we do data assimilation is that the error in a forecast tends to grow as you go further and further into the future. One way of saying that is that our forecast models and probably the physical systems are chaotic. That's imprecise, but it's a term that tends to get used. And so we use a particular class of methods to deal with this uncertainty, and that is that we do an ensemble, a word to mean a set of forecasts. And that's what all those different lines on the topographic map were. There was one from each of 20 forecasts in that picture. And we like to view these as the same way as you would view getting the batting average of a hitter, okay? Gets up once, he hits a home run, okay? He's batting 100, but you probably don't think that he's going to hit a home run every other time he's up. And so you look at his first 30 at-bats, and he comes up at, 312, okay? The same way we're going to do here is we're going to take a sample of the different possible outcomes of our forecasts and look at those samples, both their mean, which would be the 312 average, but also the way they're distributed to learn more about the uncertainty in the problems we're dealing with. Is there a question? Sorry. Okay. So it's always good to see Ed. It's too bad he's no longer with us, but it was great when he was here. So Ed here, one of the things we do a lot of in data assimilation science development is that we work with simplified models that help us to study key aspects of what we believe occur in the big Earth system models that is our final target. And back in 1963, actually a little bit earlier than that, the model itself was developed, Ed came up with a very, very simple model that is extremely powerful still for us doing this type of research. It was built as a model of convection. It only has 3 variables, which you can call x, y, and z. And one way to think about it, which I like to do, is that instead of, and I know I'm supposed to stay there, but I like to walk. So instead of just thinking of this as convection, this is really the path of a ball in a 3-dimensional space. So it goes around here for a while, it goes around here for a while, and this is 3-dimensional, so it kind of looks like this. So we're going to do some example of ensemble data assimilation quickly here in this 3-dimensional system because it's easy to view. In this example, we'll use 20 ensemble members, so 20 separate forecasts. And because there is no real Lorentz 63 system, like the real atmosphere outside the building here, we will simulate truth. We will do one run of the model, which we say, this is what really happened. Then we're going to take some observations, which will be taking periodically that true value and adding some noise that simulates observational error. And then we'll try to assimilate those observations and see if we can get back close to the truth. Okay. So now, okay. So what we're going to do here is there's 2 panels that you can view here. The top one, both of these are pictures of Lorentz 63. The top one here, you see this black asterisk, and then there's a bunch of little dots which are hard to see. There's 20 of them, our 20 ensemble members. So we're starting out here with the truth at the black and random noise that gives our best guess, which came from who knows where, to start out our project here. This is going to be as if we're in an airplane flying along with the truth and looking out the window to see how it evolves. And this panel down here will give us a bigger picture view so we can see where we are in that Lorentz 63 attractor. And this will become obvious in a moment. I am not all that excited about the spinning red wheel here. It does feel bad. Okay. I'm dead. I can move the spinning wheel, but I cannot escape from it or anything else. If you want to come try anything, that's what we're here for. We did try this because we were nervous about this work, and we tried it multiple times. So it's somebody's law here. It's just completely dead, right? So see if you kill the MATLAB. Okay, so I don't have time to waste here. So while Tim's working on that, I'm going to tell you what you would have seen, and if we get there, we do, and if we don't, we don't. So because this model has chaotic behavior, we would see as we started doing a forecast of this black dot that it would start moving around those 2 lobes of that Lorentz attractor. And as it moved, it would follow a track like this. And these 20 green ones would kind of approximate that track. But as time goes on, see if you can start MATLAB again. As time goes on, the distance between those 20 green ones and the black one is going to grow. It'll grow in a sort of systematic fashion because the green ones have to stay on that attractor, the 2 lobes too, but they will gradually spread out. And as enough time goes by with the forecast, some of those 20 green ones will decide to go into the wrong lobe, the wrong hand here. So the truth may be going around a few times in this hand, 5 of the green ones may be over here. And so as you go further and further in time, you get more and more growth of this error. Your forecast gets less and less accurate compared to the black truth. Now, what we're going to do is this cycling data assimilation, and that is, as I said, we're going to generate an observation, a noisy estimate of the truth, periodically, and that we're then going to use it with ensemble data assimilation to pull the green dots back in towards the truth so we have a better estimate, and then a subsequent forecast from that will be much more accurate than it would have been if we just had this long run. I'm optimistic here that we're about to get this. It's run Lorentz 63. Let's not full screen it that time. That's the one thing that we hadn't done a lot before. Okay, so what I'm going to do when this comes back up is I'm just going to run a quick example where you can see this thing spread out. And then we'll turn on data assimilation in a minute. Just hit advance model once. So there's one step moving forward. And I'm just going to let it continue cycling through this. Cool. Thanks, Tim. One of the things this demonstrates, by the way, is I no longer know how to do anything except kind of give publicity talks like this. And one other thing, I know who on the team can fix a particular problem, okay? And that's very useful. So you can see here, this is the big picture of where the truth is around the two lobes. And you can see the green things are gradually dispersing here. And one of the things that's going to happen, these guys, 3 or 4 of them just went this way. The truth and 16 or 17 went that way. So we're just seeing more and more error growth. Okay, so this forecast becomes less and less useful. The forecast, remember, is the green dots. Okay, so I'm going to stop this thing for a minute. And I'm going to turn on a particular flavor of ensemble data assimilation. And the observation, by the way, is sitting there in the red asterisk. And you can see that it looks like it's close to the truth. But in fact, if we rotate through space here, the red is not all that close. It's a fairly noisy observation. So now I'm going to use an ensemble algorithm to assimilate observations. Many of the other green ones were all the way off the screen. Wow, that is a bizarre magenta we got there. Many of them were way off the screen in other places, and so they have been, because they're so uncertain, pulled in very quickly towards this observation, and you can see these. So the new positions of the greens are going to be at the end of these purple magenta things which show the update from the data assimilation. So now I can make a forecast. You can see that the greens are much closer than they were before that assimilation step. I can now assimilate again. This might be every 6 hours in a weather model, and so you can see things are continuing to pull in closer towards the observation and the truth. And I would continue to cycle through that as how ensemble data assimilation would work. And again, a lot of interesting things are happening here. I won't go into details, but in particular, oops, I turned it off. Remember that the Lorentz attractor is actually fairly flat. It's these 2 sheets. And you can see if I rotate the view here, that the observation is way off the attractor, but the combination of the information from the model, which knows about the attractor, and the observation, which is cutting down the noise, has led to a much, much better estimate that's nearly on the attractor. All of these things are the benefits of ensemble data assimilation. I could talk to anyone who wants to know more. Many of the people in the room do know more. And those of you who don't, I could talk more. And are there any questions at this point from the CISL colleagues here? Okay, cool. So our moment presentation again.
So one quick question.
Yeah.
Because I love this kind of stuff. You said sort of in passing that the further away the estimate was, kind of like the more uncertain it was, and therefore the more it moved. Is that what you meant to say?
I did. So the more uncertain the... Yeah, so the question was this comment I made about uncertainty of the model. We good? Okay, and that was that we're combining 2 pieces of information, one an observation with some uncertainty, one the model, the 20 guesses with some uncertainty. And we're going to use Bayes for that. And so something that is uncertain will not get nearly as much weight as something is certain. If you have much more information, we're going to give more weight to that information. Does that kind of help? Yeah. It is not. So the green dots don't leave the planes until the data assimilation encourages them to do that. So if I had more time to show you detail, we would see there was an intermediate period when I first started doing data assimilation where the updated green dots were not on the plane, and gradually they went back onto the plane too. Yep.
So when you were showing the observation was being assimilated.
Keep going though. Okay.
Okay. So the observation was the magenta star, but the true trajectory was the black line. Was that being assimilated into that line as well?
Yeah, so the black line was not being affected by the observations. It's the truth. In other words, it's the analogy for the real world, which we can't influence with observations. It's only our estimate that we can influence with the observations. Okay. This was the, if we really had crisis with the MATLAB, that was the way to get around that. Quickly now, a cartoon of how ensemble data assimilation works schematically. And again, sorry, people watching on the recording. This is an example of a cartoon with 3 ensemble members, and maybe at last night at midnight, we had some model initial conditions. We run a forecast out to this morning, okay, time TK plus 1, where we have some observations available. I'm going to take those observations one at a time. The first one is the temperature from the mast out on the top of the Mesa lab. And I'm going to say, maybe this is gridded temperatures. And so to get an estimate from the model of that mast, I'm going to interpolate in space to the location of the mast. And I get these 3 estimates of the temperature. I get the value from the thermometer that's out on the mast, and from the guys who built it, I get an estimate, the red, of the uncertainty of that observation. I do some statistics, which I'm not going to talk about the details today, which says that, well, your estimate should probably be closer to the observation, okay? But we're still uncertainty, we just don't collapse to the observation. So I get some increments, which are shown in blue arrows there, for my estimate of the temperature outside. And then the way Ensemble DA works in general is that we simply regress those increments. It's simply a least squares fit onto each one of the variables in the model, say gridded temperatures. We just do those one by one, okay? And we can do them entirely independently. Think parallelism here for the CISL folks. I keep doing that for each observation that was available this morning. Maybe there's an observation from CU or something. Maybe there's a wind observation. And when I'm done with all those observations, then I'm ready to make a forecast out to the future. Maybe 6 hours from now, I'm going to stop that forecast again and update it with new observations also. But this is the basic way we do this ensemble data assimilation. So now I'm going to focus back in on DARES, the Data Assimilation Research section. So our mission statement, approximately, because this is bad to admit in front of your management, I couldn't actually find our mission statement exactly. I got to find it. This is a very close approximation. Basically, our goal is to move forward Earth system science, specifically within NCAR and the UCAR community, but also for anybody else who wants to play nicely, by using ensemble data assimilation, by providing tools and expertise to do it. And the tools that we provide are something called the Data Assimilation Research Testbed. Okay, so what is DART? So DART is primarily for geoscience data assimilation that uses these ensemble methods. It is extremely flexible. It has been broadly used. The software has been under continuous development for 18 years now. It works with a ton of models. We'll talk about that. Many, many dozens of large models. It works with a wide suite of observations. Those can be real, like the temperature out on the mast. Those can be synthetic, like the little red asterisk in the Lorenz 63 system. And in particular, they can be novel. Okay, new type of observation. Maybe the satellite hasn't even been launched yet, but we want to evaluate what it might do. It is a system that allows you to do data assimilation research. So members of the team and our collaborators, mostly in the university community on research data assimilation, use it to try out new techniques, maybe starting in that Lorenz 63 model and then moving from there. It is professionally software engineered, so we have certified, trained software engineers on the team. Also, our associate scientists and others have worked very hard to develop their engineering skills. It is performance portable, so it works on a lot of platforms very well. And it comes with a whole bunch of documentation examples and tutorials. As an example, that Lorenz 63 GUI that you just saw is one early piece in one of our tutorials. Okay, it allows people to quickly play around, and normally it doesn't crash. I think that had to do with the projector. And finally, the DARES team, which I'm going to highlight as we move forward. This slide is old. I was too lazy to update it, so I think now we're actually in use at something close to 70 UCAR member universities that have one time or another used DART that we're aware of, and it's really closer to 200 other sites through the history of the project now. Lots and lots of users within NCAR, which we'll see a lot about in upcoming slides too. So DART works with nearly all NCAR community models, okay, and hopefully soon with all again. There's evolution always going on. Our propaganda bullet says that new models can be added in weeks, and that's true mechanistically. Actually getting a model to work well with data assimilation is often a research problem, and that'll become apparent later on. But from a software perspective, it can be done. Same for observations. And the combination of these different pieces, observations, model, and assimilation tools or algorithms, you can basically shuffle those up. Try a new algorithm with my model, add some new observations to somebody else's model. The goal, again, consistent with the mission statement, is we want to let prediction scientists, observationalists, people who are not masters of data assimilation. We want to provide the power of data assimilation to these people with a minimum cost to their research program. And of course, I've already mentioned it has to be fast and efficient, running from this all the way up to Cheyenne, DOE machines, NASA machines, whatever. I'll come back to this list. I don't want people to really focus on it now, but you can do a lot of things with data assimilation besides just get initial conditions for forecasts. And we will give an example of all of these particular ones, and I'll focus back on them. But the key point of this slide is it does a lot more than just numerical weather prediction. Quickly, again, sort of for the CISL, some of the CISL folks here, DART has been around for nearly 2 decades. For the first decade of its existence, there was nothing else that looked anything like it. There just wasn't anything. You couldn't go to a system that did data assimilation for multiple models. The last 10 years, people have been trying to build such systems. In fact, with the NCAR now, there's a project called JEDI going on that looks a little bit like DART in some ways. There's been some European groups that have done it. But none of them have provided the ease of implementation and the broad user community we've had to date. And that's 2 critical engineering choices, which actually look kind of like Luddite choices sometimes if you're a software engineer. We thought about these things. They're not Luddite choices. But the first one that's truly important is that we don't put our fingers into the forecast model. If you come to us with a model that does forecasts, there are no software changes to your code to put it in and build a prediction system with DART. The second one is that we have greatly simplified, from an analytic perspective, the problem. This was mentioned in that little cartoon with the 3 arrows and all. I didn't highlight it there. But it turns out that without loss of generality, it is possible to think about almost everything in ensemble data assimilation by asking the question, if I have one observation and one model state variable, what's going to happen? And almost all of the DART algorithms are phrased in that way. It makes it extremely simple to think about the system compared to other systems and analytic perspectives which involve many, many matrix transformations. Okay, linear algebra, which I don't like. As an example, I have a 2001 paper which starts to develop this single observation thing, and it has a matrix equation where there are 37 matrices stacked up. So there's 18 on one side, a thing in the middle, and then 18 transposes on the other side. Okay, I don't like that. I can't think about that. I can't remember how to do it. Okay, so this simplifies our algorithm development and our parallelism. So I'm going to change gears now. I'm going to tell you some stories about 8 different projects. The level of, oh, sorry, Seth, go ahead. John, run the mic up there.
So does that second point mean that you can does that mean the observations have to be observations of state variables, or can you sort of get a transform back to it? And are there like limits on which kinds of observations are usable? Like, does it sometimes get too hard to map back and forth?
The easy answer is no and no.
Okay.
So it is completely general. The observation, all we need is that H operator, which was in the slide. We have to be able to say, if you have the model state, say Chem variables, you have to be able to say what you think that instrument would measure. If you can't do that, then you can't use the observation. If you can do that, you can use the observation, and the complexity of the relationship doesn't affect your ability to try to use it. It may affect the quality of the results. Okay, so these science tales now, there'll be some long ones at the start. I'll then run out of time, and John will start making frantic 5-minute signals to me, at which point I'll go faster. I could have picked, when I started doing the list for this, I came up with more than 100 projects. So this is a microcosm of what we're doing. It's certainly some high visibility ones. So I'm going to start with the ones that look like the most widespread applications across data assimilation. So Glenn Roming, who's got a 50% joint appointment with M cubed, Glenn's here. He's been with the team since 2009, and this project uses the weather research and forecasting model, M cube's sort of regional model, to do ensemble prediction. It is basically doing the same thing that the operational weather centers do without the operational part, which meant that if things did get messed up, Glenn didn't get up at 2 a.m. and call the whole team. But it didn't get messed up too often, right? Yeah, right. So this system ran for a number of years. This is just an example from the web page that went with the system. It was a beautiful web page, which DARES did not develop, but other collaborators with Glenn did. And this is just a picture of the Ensemble mean 6-hour forecast of snowfall that's going to occur on a day. You can't read it, but it's 6th of March, 2017. So it's snowing in the Wasatch, snowing in the Sierras, coastal range. That's the forecast. They generated a huge number of products for people to look at, and they went public with this in that weather service forecasters, people at the University at Oklahoma who do research on this type of prediction were able to look at it. This is just an example. Severe weather is a big deal with these folks. And this is using the Ensemble, not just the mean, but now making a probabilistic forecast. This is saying a certain fraction of the Ensemble members think that there's a potential for severe weather, and the color coding tells you what the potential of that severe weather is. This is a 2-day forecast. So the color coding is a forecast probability, and on top are little symbols which you can't see very well, which are actual reports of severe weather that occurred during this verifying period. And so what you're happy to see is that where we had higher probability of these types of severe events, these things occurred. Am I okay on the way I describe this? Okay, Glenn's not entirely happy with my description, but it gives you a basic flavor for what's going on. An important point here is that CISL provided tons of computational support for this, dedicated queues and support to make this type of project work. Okay, a second example, we're going to start moving slowly away from NWP now. So the lead on this project was Kevin Rader, who's been with the team essentially since its inception in 2003, but has been with NCAR, with CGD before that, for a long, long time. This is using the newest version of the CAM, the Community Atmosphere Model from CGD, embedded in the whole coupled Earth system model system. So this is being done in a coupled prediction system. There are a variety of university collaborators, and it's an ensemble reanalysis. So a reanalysis is basically just doing weather prediction after the fact, and generally over a long period. And the reason we want to do this is a couple science motivators. One is to just look at how CAM's doing. Okay, we can compare CAM to observations as a weather prediction model. It's built as a climate model, okay, but it's not all bad to have your climate model be able to predict weather too. We can also look at how it compares to previous reanalyses and various other things. So this can help inform the developers and users of CAM itself. Also very important for many, many other model components of the Earth system. If you want to do ensemble data assimilation in these models, it is essential to provide enough uncertainty in the model. That had to do with the question about how much weight do you give to the model forecast, the ensemble versus the observation. If the model forecasts are all very similar, then you will end up ignoring the observations because the data assimilation says, I already know what's going on. The model says it's this, it's almost all there. And it turns out that having a variety of forcing from an ensemble reanalysis with CAM, for instance, is essential to allowing ensemble data assimilation in a variety of other models. So this particular thing right now, we are currently running this new reanalysis. It's going to go from 99 to the present. It's really, really, really expensive. It's really, really, really hard. So thanks to many people from CISL for helping us keep this running. Kevin basically works through the nights, through the weekends, all the time, keeping this thing moving. We assimilate a bunch of observations, and this just gives you a feel. These are things from GPS satellites. These are radiosondes, so balloon temperature and winds. Your planes, when you're flying, are taking measurements. We're getting measurements from satellites of winds and a variety of other things. So these types of observations are getting assimilated into the CAM model. The model itself is at a 1-degree resolution. This is the same resolution run for CMIP6, which I know many of the CISL folks are familiar with. And this is just an example of what you get. This is a particular analysis, 13th of September 2010. The black curve is the operational NCEP analysis, so a high quality weather center prediction product. And in this case, 20 out of 80 lines below are from our reanalysis. You may say, well, gee, there's a lot of junk here in the tropics. The answer is that that's because we all know almost nothing about what's going on in the tropics for a field like this, which is the height of the 500 millibar or hectopascal surface. On the other hand, we know quite a lot about what's going on other places. As an example here, off the coast of Africa, this is tropical depression, soon to be tropical storm Julia in an African easterly wave. This was going to be the furthest east category 4 hurricane in the Atlantic. Harder to see is Hurricane Igor, just gone to a Category 1 here, moving off towards North America. And if you just blow up to get an idea of what's going on here, you can see the relationship between the black operational product from NCEP and our ensemble. So in places where we're quite certain the operational one lies in it, in other places there's a lot of uncertainty and still the operational lies in it. The value of the ensemble product here cannot be exaggerated. Having a single estimate is not very informative on anything, so having this ensemble really helps our users. Example number 3, led by Moha, who's been with us since 2016, and one of our new staff. One good thing about the timing for this is we've just come back to full staff for the first time in years and years, and we're really excited about our new folks getting moving. So Ben's been with us since September. This is using a model called Worf Hydro, which is nearly the same as the Operational Weather Service National Water Model. And we're collaborating with RAL, in particular James McCrate, some folks at universities. And I'm going to key on a capability of data assimilation to do model improvement here. Basically, Worf Hydro takes some input from a weather model about how much it's raining and stuff. It has a land surface model that does some stuff with that rain and with temperatures at the surface. It knows something about the orography, so how things slope, and where stream beds are located. So basically it takes water that falls into it and either up on the surface or below the surface, it runs that water into streams and then it runs the water down the streams. And so Moha and Ben and other members of the team, by the way, the team works very broadly, so I'm keen on a particular person with any project, but every member of the team is involved in one way or another with every project. So they've been building a data assimilation system here which focuses on 2 parts of the model. One is the actual amount of water that's flowing down stream beds, and one is how much water is sitting in the land at a particular place. And that's modeled by something that was developed way back in the 70s by Manabe at GFDL. It's just a bucket. So you think if you have a bucket that's filled with earth, you pour water in it. If the bucket gets too full, it flows off. If it's not full enough, it can take some more. And so they've been doing data assimilation with this. I'll just show a particular case. This is landfall of Hurricane Florence, which did a ton of damage. Most of the damage wasn't from the high winds. It was actually from flooding, both from storm surge, but also from stream flooding. And you can see that dumping 30 inches of rain in a stream probably isn't the best way to avoid flooding. So this is a feeling of the domain. I hadn't realized before that this slide shows me how to walk across the domain. So it's 147 miles from Google Earth, so I don't pay enough attention. So that's basically where this model is working right now. And this is a model of all the streams in that area. What we're going to show here is if you don't do data assimilation, if you just let Worf Hydro get the information it gets from the weather model, this is the stream flow you get during the middle of September. But if you do data assimilation, where you take observations at all these different stream gauges, so those have a volume of water flowing down them, and so if you assimilate those observations, these are the changes you get in the stream flow. And so in general, there are massive increases in the amount of water flowing down a number of these drainages that you're able to detect, and then you could also go ahead and forecast them by using the observations and doing data assimilation. So this is quite a bit different from an atmospheric application. And the thing I wanted to highlight here, we've done this in many other applications, but this one is recent. One of the things that came out of this is that the forecasts from the model didn't agree very well with the observations. And so DART kept saying, oh, you know, these things don't agree very well. I've really got to stretch to make the model look closer to the observations. It turned out that this revealed some misconceptions about how the bucket was being applied within the model, clarified some things that required changes in the model. And so this is an example of how confronting a model with observational data can lead to detection and subsequent improvement of the model capability. So we talk about this a lot, using data assimilation to improve models. It's important to realize that this is still pretty darn hard. And so you have to have a good collaborative relationship between the observation people, the modelers, and the data assimilation folks to make this happen. But it's pretty exciting and pretty powerful when it does happen. Okay, project number 4, led by Tim Hoare, who's been with us since 2003 and was with GSP before that, again for a long time. So we're bringing in new blood here. Sorry, Tim. Another thing we do is we work a lot with long-term visitors. And so Shirley Huo is with us. She is replacing Andy Fox, who sat with us as a long-term visitor for more than 3 years and is currently down with JEDI at UCAR. And so she recently joined us too. And this project is working with the community land model. That's the land component of the climate model. And I suppose I should say CTSM if I were being politically correct. But, and I'm going to focus here on a predictability application of data assimilation. Now, this gives you an idea for what's starting to happen with models here. This is a schematic of an earlier version of CLM 4.5, which is the one this particular set of results was done in. These are massively complex systems. Okay? They are not necessarily predicated on something nice like Navier or Stokes either. And so there's a lot of complexity here. And it does a ton of stuff. So there's snowfall over here, there's soil moisture, there's all these exchanges of radiation. Here's more of the water stuff, so water going in through plants, through the soil and everything else. It models vegetation, so what's going on with trees and plants. And the particular example I'm going to show you here, we've done data assimilation with different collaborators on all aspects of these figures, but the results here are actually looking at if we have observations, remote sensing observations or in situ observations of what's going on in the atmosphere, what can we learn about how much carbon is hanging around in different parts of the forest, basically. So as I said, this work was done in collaboration with Andy Fox, who was a long-term visitor. He started out working up at Niwot Ridge, so CU has a observational site there. So this is nice because many of us are familiar with this geography here. And in particular, he started out just doing a single column, what's going on at this one spot in the Front Range. And he assimilated a bunch of observations from the towers and other things they have up there. And in particular, this is stressing a point I made earlier, it was essential to have this forcing from the other reanalysis. So our earlier CAM reanalysis was essential here. And one of the things he found was for a bunch of different things in the CLM model, like leaf carbon, root carbon, dead stem carbon, soil carbon, soil liquid, all these different things, which are completely unobserved at the moment, he was able to say, well, if we have the observations we have in this model, the suggestion is that we can predict these quantities with this degree of certainty. Okay, so this is exploratory. This is not confirmed because these things weren't observed, but it at least tells you as a preliminary step, these are some things I might be able to predict with the observations I have and with the model I have. Now I need to explore it more. And the next step, of course, on that is to go from a single column to a global application, and those steps are underway with projects related to this now. These are some initial examples of that. Okay, example 5, I put myself down as the lead on this because I wanted to mention my name once, but Nick, are you still, Nick's still here. HAO, Nick Petitella is the one doing all the work, and to be quite honest, Kevin probably does most of the work on our side too, but I wanted to put my name on a slide. And I have been with DARES, so I came here in 2001 with my own money for 2 years to try and build this thing, so I've been here a while. This particular one, I'm going to focus on observing system evaluation capability. Again, hopefully I'll get close to right. Yeah, fat chance on that. So this is in the WAC-MX model, so it is a version of CAM. It's slightly coarser than what we saw before, 2 degrees, but it goes really, really high. So basically up to 500, 600, 700 kilometers. Am I good there? Okay. There's a bunch of details in the model that aren't necessarily important, but what Nick has been doing is he's been assimilating all the observations we saw for the reanalysis in the troposphere and stratosphere, but then he's also got some remote sensing observations of temperature in the mesosphere, basically. But he's interested in the ionosphere, and so he has no observations high up in the ionosphere. So this is again an example of what can I learn about things where I'm not using those observations in the assimilation. And this is just a particular example looking at a stratospheric sudden warming that happened in January of 2015. And what you're seeing here is a height latitude cross-section at a particular, sorry, that's entirely wrong. A latitude time cross-section at a particular longitude, and this is of a quantity called total electron content, which is how many ionized electrons in some sense there are looking all the way down through a column. This is a forecast that was started here. This is the reanalysis that was generated with DART, so this starts from here. And this is independent measurements of TEC. And the research here is showing that these observations of the lower atmosphere are able to give informative information that can give you a meaningful forecast of TEC up in the ionosphere. So there's lots and lots of other science underlying this. Hopefully we're giving Nick a tool that helps him to learn more about these things. Example 6, and since I'm down to 4 minutes already and I have 87 more slides, we'll speed it up a little bit. I wanted to mention this one because Arthur Mitzi, this was a big project for Al, so this was the last thing he worked on with us before he passed away, is setting up this joint position with ACOM, developing data assimilation for the Worf Chem model. So this is the Worf model with a chemistry capability. And there's lots and lots and lots of ongoing collaborations right now. Arthur is currently with the state of Colorado, but he's still collaborating closely and leading the development of this model. The particular project I'm going to show I picked because it's in the Denver metro area. It was picked to be in the Denver metro area because there's some field projects that took place here that motivated this. But this is an observing system simulation experiment. Again, there's no real data here. It is simulated data. And the question is, if I have satellite measures of NO2 and I have some surface measurements of NO2, can I actually say where the NO2 is coming from? Okay? How much is being emitted where? Again, we won't go into the details at this point, but this is the type of domain that's used. So you can see the continental outlines here. And so we have a nested model. There's higher and higher resolution in Worf Chem all the way down to a kilometer. Actually, I think it's 3 kilometers in the white and a kilometer in the red is the final weight they used. That's a simulated NO2 concentration. You can see the major cities there, including Denver in the box. And if you zoom in the box, this is saying, if I gave the model a particular NO2, the same way I did the black asterisk in Lorenz 63, can I recreate where that NO2 came from just using the observations? And here the answer is yes, you can to some extent. And those of you who are familiar with the area will see the interstates. Okay, so there's 25, there's 70 going up the canyon. This is Denver Metro. This is down into Tech Center and everything else. So getting source sinks emissions, doing chemistry assimilation. We have other collaborations with folks in ACOM. Ben Gobert's here at the moment on larger scales. This is a huge, important growth area for data assimilation applications. Okay, number 7. Jeff Stewart, who also joined us recently in September. He's here because Nancy is jumping ship, so she's retiring in a few more months. This is using, and this one's just so cool. It gives you an example of some of the stuff we do outside of NCAR. These folks from JPL called me up last year and said, we'd like to try and explore predicting tsunamis with this model we have. And for now, this is really tenuous, okay? We're not sure if this is going to work. We're not sure if the models are good enough, if the data is good enough, but we're going to explore it. We work these types of projects. They're going to visit us next week. I visited them to talk about the initial science a few months ago. 2 of their team members are just going to come in bed with our team next week, and that's how we do these initial collaborations. But the thing they're doing, I just couldn't believe it when I first saw it. Some of you may not have the same reaction. But so tsunamis, big tsunamis, may modify the sea surface in the open ocean by tens of centimeters. Okay? So that forces the bottom of the atmosphere. And it turns out because of the horizontal scale of these sea surface perturbations, those waves amplify as gravity waves as they propagate vertically in the atmosphere. And by the time they get to the ionosphere, a few hundred kilometers up, several hundred kilometers up, the amplitude can be much larger. So it can be hundreds of meters. And it moves around the ionized content of the ionosphere, this total electron content we mentioned to go with Nick. So it moves that around. Well, when your GPS signals are coming from satellites down to your device, it turns out one of the things they're slowed down by is these ions in the ionosphere. And the crazy thing is this, if you have a special GPS ground station, you can actually measure how much the ionosphere has been bumped up and down by these waves that are forced by a 20 centimeter change in sea surface height. And I didn't believe it at first, but they have proof. So this is from the Tohoku Tsunami in Japan. What is here, this was the epicenter of the earthquake, so the waves are propagating out in a circle essentially. And these stripes here in the colors are actually the delay in ground-based GPS. And you can see they're only located where there are actually ground stations to see the GPS signal coming in. But the goal of this project is to actually assimilate in a model of the ionosphere these delays in the electron content reduce thing, and from that, go back and figure out what the tsunami heights are, and from there, be able to predict what the heights are going to be as it moves inland. Okay, I'm way over, but last project, and I will be able to skip the stuff I wanted to skip. Dan Amrine just joined us. He's an 80% CGD, 20% with us. He comes and visits our software stand-ups. He's going to be working on developing coupled DA for the Earth system. So that will be ocean, atmosphere, land, and ice. Okay, so we have done preliminary work on that with Alicia Karspek, who was in CGD and left us several years ago. I'm not going to go through the details of that project now, since these are the old results, but suffice it to say, we did initial work on this. We are excited about doing new work with it with Dan, and that project is underway. We're going to start some actual new implementation in about 2 weeks. Okay, I'm going to skip this stuff. I said I might anyway, but another thing that DARES does is we develop improved algorithms. So we want to make our Ensemble data assimilation work really well for our science collaborators. We have a history of innovative algorithms that make Ensemble DA work better for lower cost and more efficiently, and those are widely used in almost all DART applications. Okay. We're continuing to work on particular problems. As an example, almost all the algorithms we have right now assume that we can fit a normal distribution, so mean and standard deviation, to our ensemble. And as was mentioned in answer to Seth's question, they use linear regression, plain and simple, to figure out the relationship between observations and state variables. Turns out that current research is leading to getting rid of some of those assumptions. Both Moha and I are working on new algorithms that are in various phases of testing. Moha's in particular has shown big impacts on improving the stream flow in that example I showed you earlier with Florence, and that's because a bounded quantity, stream flow, only goes to 0, doesn't go back upstream, is very non-Gaussian. And these algorithms seem to be really useful there. Okay, so finally, it's a CISL seminar. I wanted to highlight some of our interactions with CISL quickly. The names aren't enough, they never are in these things, but this is just an example of CISL colleagues who've been working with us on optimization, algorithm analysis, keeping this crazy reanalysis going, starting to explore machine learning interaction with data assimilation. Observations. We're getting observations of the ocean, atmosphere, all these other things, and many of those are coming from CISL curated collections. Okay, CISL has a big data part, so really, really big data. We have the biggest data, okay? So whatever you have, if you have observations, we're going to make 80 copies of those for ensembles. If you have a model state, we're going to make 80 copies of that, okay? So whatever you have, we're bigger, okay? Okay, for the same reason, lots and lots of supercomputing resources, lots of need for optimization. This machine learning thing has been on the floor forever, and we're starting to explore that, so initial things there. SciPark students, we really, really like working with the SciPark students. We love our other visitors too. We have a couple of our other visitors, ASP visitors are in the room right now, so Michael and, I don't see Joseph at the moment. Okay, Joseph, sorry. Okay, so we really love visitors. We've been averaging about 15 visitors a year for the last 3 or 4 years now. Okay, and one other question which was probably going to come up, I'm just going to take it off, is why the heck are we in CISL? Okay, so the original answer was we were in CISL because Tim Killeen needed something on an org chart. Okay, but that's not the good answer anymore, because for reasons that were never quite clear to me, our management was extremely generous to us 2 years ago after Image went away. And they gave us the opportunity to explore where we thought we would fit best in the organization. So that's really, really generous. My only thought was that maybe they were hoping we would go to M-cubed and they could trade us for a future draft pick or an ASP postdoc, but whatever. But we took advantage of that. So we carefully explored throughout the NCAR organization where we wanted to be. And here we are, because we think that this is the best place for us to be. We are a little bit out of the politics of the science and model labs, and we get great, great support from CISL. So finally, where are we going? Some projects coming up. I already talked about coupled, so we're going to go to new types of fully coupled assimilation for the Earth system with CGD. Satellite radiance observation, so that's looking at exactly what the satellite sees when light comes back up. We need a capability for that. Jeff's going to be leading that project. We're going to develop new software to handle observations. Right now, in particular, we can't handle correlated observations very well, and that is a hot topic in improving data assimilation. We have to keep up with the Joneses here, so NCAR moving to SEMA, so a unified modeling system. We're pretty much ready to go with that, but we will continue to keep up with that. Same thing for the new chemistry modeling. And for MPAS, where we have a really good active collaboration with So Young Ha at this point. And finally, really one of our goals is that when something cool like Tsunamis comes along, or when someone discovers something really interesting about what's going on with the stratosphere in Chem or something else, our goal is to stay nimble enough so that we can collaborate with those projects effectively and quickly. So whatever it takes for us to be able to keep doing that is a priority. And so, okay, a bit over, but not too bad. There were some questions during. Okay, thank you, everyone.